Hello, can you see the screen?
Yes, sir.
Okay. Okay, so in our last class, we were discussing about the problem of data access synchronization, and what we found is if we write high-level languages, high-level instructions, then actual instruction may be uh, in the background. After compilation, it may consist of multiple uh, hardware instructions, and uh, there can be, while executing that, there can be interrupts, timer interrupts, which can preempt that particular process. So if I consider a particular simple incrementation of a variable, a shared variable, by some amount, if I consider it to be a very small instruction, very simple instruction, that too might be interrupted while it is trying to read, update, and write onto the memory location. And whenever multiple processes try to do the same uh, on that particular shared variable, that might lead to inconsistency, and that is what we call as race condition. And what we found is if there is such race conditions that arises, we call it as critical sections. Okay, so critical section, uh, say if you have got access to a shared variable in your entire function, you may try to consider the whole function to be critical, or you may try to specify that particular instruction or statement where it involves the access to the shared resource as critical. So it's up to you. So let us assume that we specify those statements to be critical. And why it is critical? Because until unless they are handled properly, that might lead to inconsistency. So what we found is whenever we think of, so there should be some mechanism which will try to address this and will resolve these problems, even though sharing of resources is allowed and multiple processes can concurrently do that. So the simple assumptions are relative speed. We cannot assume that some processes are we will be getting more CPU, less CPU. So no assumptions are made during the solution. No indivisibility. We cannot assume that even if it is a small instruction, high level instruction, this should be atomic. So no such assumptions programmer can make. And bounded use, any process which is accessing or which is inside the critical section, means it is accessing that critical resource, it is assumed that it will be eventually releasing it. So it is not so this is not a kind of a security problem that it holds and it never gives it off. So they are fair in the sense, if they enter into the critical section, so within a finite time that uh, they will exit the critical section and allow others to also use it. And the mechanisms, whatever the solutions we design, they must follow these conditions: mutual exclusion. So because this is a shared resource, we know that it should be accessed in a mutually exclusive way, so we cannot force that. So this is one primary requirement, and which makes the problem non-trivial. Progress, this, so in this class we'll see some examples to which we see that although it seems to be very trivial conditions, but there are cases where even these few simple conditions it becomes difficult to satisfy, and that becomes a challenge to propose solutions. So what progress means? If one process uh, say is willing to access the critical resource, say maybe every second, but the other processes are willing to access it once in an hour, so it doesn't matter in what pace they should use, so they should be able to, so the process which wants to access it more frequently should be allowed to do that without getting interfered by the other processes pace in entering the critical section. And definitely because you are probably having some kind of some other variables to which you try to access it, so it should be deadlock free, and it should be light block free also. So we'll see the cases as it occurs. So in this class we'll be mainly talking about the algorithmic approach here, okay, in this class. And then later on we'll talk about the same solving the same problem using semaphores and monitors. So this first approach, as you can see here, there is a shared resource R. Okay, so this R can be anything. This can be an integer, this can be a file record. So this is shared, this is a shared resource. And as you can see that CSR is the critical section corresponding to two processes. So this is process P0 and this is process P1. So there are two processes, P0 and P1, and each of them they have got a critical section CSR. So this critical section is associated with the access to the critical resource R. So as you can see here, there are multiple instructions here and there will be multiple instructions later on also. So this is the point where they access the critical resource. And there is a typical statement that I have written here. Parent means parallel end. So this is just to denote, this is not a C level function. This is just to denote that this par begin means P0 P1 means, that means at this stage we would like to access, like to ensure that P0 P1 are both concurrently getting executed. So this is what it means. So both process runs simultaneously. So this is the P0's code, this is the P1's code, both will run simultaneously, that's all. And both have the same critical section associated with R. So the simple logic is, and this while one means, so they repeatedly will try to enter into the critical section, okay. So they repeatedly will try to enter into the critical section multiple times. So the idea is, now in this case, now we have to ensure that when P0 is accessing critical section, P1 should not enter and vice versa. So the simplest way to do this is to use another shared variable called turn, okay, and turn should get some value, maybe 0 or 1. We have initialized to 1, it to 0, and probably you can see the code. So what this P0 does, what is the intention, what it does actually in this line. Hello.
It is waiting to enter.
It is waiting to enter, but the thing is the turn plays the trick. So the value of the turn, if it is 0, that means it is P0's turn. If the value of turn is 1, it is P1's turn. That is what it means. So P0 wants to enter, this means P0 wants to enter into the critical section, but before that it checks. What it checks? Definitely there is no point of checking my own value. I should rather check whether it is the other process's turn. If it is the other process's turn, that means if turn is not equal to 0, or I could have written turn is equal to 1, then this basically waits. There is a semicolon here, that means this forces the process to wait, that's all. But if it is not the case, that means if this is if it is 0, that means it is its turn, and in case it is its turn, then it can enter in the critical section. So once it executes the critical section, means currently the value of turn is definitely 0. So after that, to be generous, or to be fair enough, and to avoid any kind of monopolization, this will set the value of turn to 1, that's all, okay. So let me use it, and after I have, so if you are not using, that it checks here, if you are not using, then I'll use the resource, and then I'll set your turn. And this process also does the same. Let me check if it is if you are using. If it is not your turn, then I'll use it and I'll set your turn. So that is what it does. So that is a very simple logic, and they will do it in parallel, and no matter in what way they are interleaved, because it might happen that this will be executed first, and then this is scheduled, then again this is scheduled, then this is scheduled, whatever it is. So whatever is interleaving, so if we consider this solution, will it ensure mutual exclusion? Will this solution ensure mutual exclusion? That means no two process, both the processes cannot access the critical section. Can it be ensured? Hello? Hello? Is that guaranteed? Are you getting me? Will it guarantee mutual exclusion? Can it happen that both the processes, like this process also is here, this process is here, and this process is here? Can it happen ever? Please answer. Hello? Are you getting, or I'm talking to the class? Can you are you getting me, or
Sir, if the comparison is of multiple statements, then problem can be occurred if one of them changes the value and the comparison is still
which
working on the
comparison?
other.
Now tell me which comparison you are talking about.
Turn not equal to 0, turn not equal to 1.
See, the point is turn is a single variable. So can it take both the values simultaneously? It will be either 0, it will be either 1, right?
Yes, sir.
So if that is the case, so can it ensure? So just noting this, can I make sure that
No, sir,
both?
I'm saying that maybe the flag variable means the conditional flags will be set after the turn is working, and the other one changes the value at that moment only.
No, are you talking about setting this initial value or what?
No, no, sir. There are set of conditional flags now after the comparison operation in assembly has flags NZVC. So Z flag if it doesn't, if it sets itself and the other core resets it means it sets it too high, then what will we do?
Now see the point. So this is the RAM, right? This is the RAM, and this is the value where the turn is stored, right? This is either 0, say this is currently 0. So
Yes, sir.
now you may have, doesn't matter what you have. So you have got one CPU or two CPU, doesn't matter. So this is P0 is running here in CPU, and in this case P1 is running here in this CPU. So this access to the memory location is serialized, right?
Yes, sir.
Access to the memory location is trivially serialized. You cannot do it parallelly. You can run it, but you cannot do it parallelly. So the thing is, if both, say, assume that both are checking for this while loop, this while loop. Now this is now 0. So who will find it to be false?
Yes.
Which process will find it to be false? P0 will find it false.
Yes, sir.
So P0 will find it false. So P0 will automatically come here, right? But
Yes, sir.
P1, what will P1 will do? P1 will get stuck here because it finds that it is not equal to 1. It will get stuck. Say for example, you have scheduled the scheduler has scheduled P1 first, right? If it has
Yes.
scheduled P1 first, then P1 will find that it is 0. It will simply wait here. It will get stuck here, and
Yes,
then
sir.
it will get suspended. So some kind, it's not suspended, it's basically busy waiting, doesn't matter. So P1 P0 will get a chance and it will find that it is 0. It will simply enter. So my point is, can both the process enter simultaneously at this position? Definitely not.
Not. Yes.
Now since P0 executes this and it comes here, it sets turn to 1, so it makes it 1,
Yes.
makes one, and then it again does something else, again comes whatever it is. Now because it is busy waiting, so whenever it gets a chance to get scheduled, it finds that it is 1. Now this will come here and will execute the CSR. But when this P0 is in CSR, you can guarantee that P1 P0 is not in its CSR. That is what I mean. because it is strictly, it can take one value. It can either be satisfied in P0 or it can be P1. So both cannot bypass this while loop and come to the CSR simultaneously. Is that fine?
Sir, but we do we have a hardware support for this shared int? Because if it's
There is
not, then
there
we
is
want.
so see, this is a pure algorithmic approach, as I mentioned. So do not assume any kind of additional hardware or specialized hardware supported for this. The
So
only
then the
assumption.
cache and the registers will revolt against this, no?
Which one?
The cache
See,
and the registers, because
hmm,
registers store these values and the optimizer will also maybe cause a problem, maybe, because cache is always problem.
no, I'm not getting. See, whatever is the case in the RAM. So the first thing is in the RAM, you have got the memory location which stores the shared variable value of turn.
Yes,
So
sir.
that is having just one copy. No matter how many CPUs you have got, how many processes are competing for this, that is having just one value.
Yes, sir. But in multiple cores we have L1 caches are for each core, then that will be a problem, I'm saying.
See, this is my point is when you are using shared memory,
Yes, sir.
let us for simplicity assume that you are not. I got your point. So you are telling that I copy it from the memory location and copy it in the cache and I keep using from that, right? Is that
Yes,
what you say? So
yes,
when
sir.
you deal with shared memory, because you are not the sole person who is using it, so there
Yes,
should
sir.
be some different, cache synchronization, or I mean cache coherence issues that need to be handled. So let us
So
assume
that need hardware support, no?
that some hardware support or some kind of protocol is required. So how the cache will be used in case you have declared something as shared. So the thing
Okay.
is, if you just declare it as intx, that will be dealt in a different way. But if you write here shared in, so it is not as simple as that. We'll show that how you can share it. But when you are dealing with shared pieces, so the way you will be utilizing the cache will be different, because then it will be cache coherence problems will occur.
Yes, sir.
You have got a shared piece. Now you have got a copy of that and I have also got a copy of that. Now I
Yes,
update it, you have not
yes,
updated it. So
yes,
now
sir.
whenever I update it, will the system go on and copy it back to the memory location, or it will defer it for some time? So those are uh, cache coherence related problems. So there are algorithms for doing it consistently. Let us assume that, okay, that is not the issue. Let us assume that there is no cache that is currently used, and make a very simple model that we have got the RAM, we have got the shared piece of data stored in some RAM location that is shared, and now processor accessing it. I got your point. I got your point, but that is a issue of cache coherence problem, which definitely will not be the same if you are dealing with shared piece of data.
Okay.
Got the point? So let us
But
first ignore those complexities, because that is, again, that is a part of cache coherence. As I mentioned, there are different algorithms to deal with it. So whenever somebody writes, will it be copied back? So whenever it is copied back, then what others will do? So they will be send some signals and you please hold on, so get a new fresh copy and do it. So those are other issues. Okay, so right now let us assume that we have got a simple model. We have got a RAM, and this is how they are accessing it. They can directly access it like that, but one by one, simultaneously they cannot do that. So now, is the multiple mutual exclusion problem resolved if I do this approach?
sir, yes, sir.
But now let us consider the progress property. Will the progress property also be satisfied through this? The problem that I mentioned, say P0 wants to access it, say once in a minute, but P1 wants to access it once in an hour. So whose space will be dominated? Whose space will dominate the progress?
The one in a minute time.
One in a second.
One in a
Sorry,
second.
one in an hour. Because you see, so the point is, it is strictly alternating. If I get my turn, I cannot re-enter it until unless you take your turn, right? You see, I take my turn, but before I leave, I set it to your turn. And if you don't enter, I cannot re-enter once again, even if I try. even if I keep trying. Got the point? So the progress is basically dominated by the slower process. Slower means which have less frequent access to the critical resource. Is that point clear? Are you getting me?
Yes, sir.
This is what happens. So here, so P1 and P0 P1 strictly alternates. Okay, P0 P1 strictly alternates, and the pace of the execution is dictated by the slower process. And at the same time, there is another problem. If one fails, say being in the critical section, if a particular process fails, then what is going to happen? Say P0 fails, terminates abnormally, and definitely this turn 1 will never be 1, and then P2 will remain indefinitely. It will get into a problem. So these are the issues or the problems of this particular case. So what is the underlying problem here? The underlying problem is that we are trying to deal with the willingness, the state of the two processes. Right now we are considering the two process solution, and we are not making the complex case of n number of processes. Even for two processes, these are the cases. So the thing is, the willingness of both the processes is basically tracked by a single variable. That is the problem. So the simple solution can be, we can think of shared int flag so we can think of having two different variables. Say we call it as now flag 0, flag 1, and we say that flag 0 will store the state of process 0 and flag 1 will store the state of process 1, right? Because now if you have, so now if the process 0 wants to enter as many times, it can do that without the other process need to enter say alternatively or one after the other. So if that is the case, how will we change this? While 1, and if this is a critical section, how we are going to modify this? So this is for process 0 and this is for process 1. How will you do this? So what it will check now here?
Maybe what we have started and I have ended two booleans.
So what it will check? What it will check actually? Both of
Is
these
the
will.
second process started or ended?
So as I mentioned, so flag false, false. Both are false now. So both are false means what I need to check that whether flag. So this P0 will check that whether flag 1 is false or flag 1 is true. If flag 1 is true, then it has to wait, right? Is that fine? P0 will check whether flag 1 is true. That means the other process is true. Other process is true means that process is willing and it has probably entered into the critical section. That is what it means. Are you getting the point?
Yes, sir.
And this process will just do the reverse, flag 0. If it equals to true, then it will wait. That's the case. Now the only difference is instead of just putting the whole thing in a single variable single variable that we earlier called turn, we just stored it in two different variables, and in a boolean variable set false, true, whatever. So if this is true, then what is going to happen? So if this condition is not true in case of P0, then what it does? It comes here. That means it is sure that the other process is not entering into the critical section. So what it will do first? The first step is it should set its willingness. So you first check that if you are not. So it's just like if you check that if you are not taking the class, then what I do? So say maybe there is a single classroom and there are two doors, and through this maybe I enter and through this maybe TD enter, right? So if I say that TD's door is open, that means he is not willing, it's false. Then I enter and close my door. And meanwhile, TD comes and finds that this door is closed, he will simply wait outside. It is something like this. So the first thing is, if I find that TD's door is open, that means this is false. So I come here and what is the first thing that I do? I should set my willingness. That means I should set flag 0 to, what should I do?
True.
It will be set into true. True means I just stop the other person to enter and I signify through that. Okay, so P0 will check this and will set this, and P1 will check this and try to set this. And once it is done, that means I know, I am sure that the other person is not willing and I have set my willingness. It will stop him. Let me just access the critical section, and before I leave, what should I do? Flag. Which flag should I set? Which flag should I set now?
The flag of other first.
Flag 0 or 1?
0 to false.
Sir, flag 1 to true.
Now, why should I? So the point is, what did I do before entering the critical section? I have set my flag to true. So before I leave, what should I do? I should just, open this door. That's all. I should open the door. If I open the door, that means that is enough for TD to know that, okay, I am not taking the class and he can enter and take the class, right? Got the point?
Yes, sir.
So let me set my flag to false, or I just open my door. That's all. And on the other hand, if TD finds that my door is set to false, that means my door is open, he will set his flag or his door to true. Now he will close the door, take the class, because say for example this classroom is the critical resource R, both wants to share, and then he will reset his flag so as false. That's all. So if this is the solution, and say we may do it multiple times in a day or multiple times in a week, we keep on doing that. Okay, so now, so first thing is what will be the initial values of flags? It may be set false false. If we set false false, so will it be, so if we set false false, will it ensure mutual exclusion?
No, sir.
Will it ensure mutual exclusion? Because you see both are false. So it says that, so it might happen, you see, that this is getting executed first while flag 1 equals to true. So P0 process is scheduled and this is getting executed. And it, after it checks that this is flag 1 is false, so it is here and it gets preempted. Now P1 gets scheduled and P1 checks for this while loop and it finds that flag 0 is also false and it is now here. So can you find the problem here? So now both has successfully bypassed that waiting condition. Both has bypassed it and both are here. So both will set their willingness because nobody stops them and both starts entering the class. So there now there is a chaos. So this simple solution, trying to dissociate the states of the two processes using two different variables, what it will end up? Will it be able to ensure mutual exclusion? Will it be able to ensure mutual exclusion? Hello?
No, sir.
So that's the case. So if this is a solution, then the mutual exclusion property cannot be ensured. So you try to resolve one problem, you get into another problem. And what about the progress property? As you can see here, each process enters. So the thing is, earlier, the problem that we face, that if I am willing to enter it once in a second and you are willing to enter it, maybe once in an hour. So I want to take class maybe every day and he wants to take class once in a week, say for example. So what is going to happen? earlier, in the earlier case, in the previous case, it was strictly alternating. So if he takes the class, only I mean, it's like handing over the key. So he hands over the key, only then I can take the class. And once I take the class, the simple protocol is you should hand over the key to him, and he can take his class in his according to his schedule. So that was the previous case. To solve it, we created two doors. There are two separate kind of locks, willingness locks or whatever. Now you create other problem, but now the problem is if he's not at all willing to take the class or he has completed the syllabus, so I can keep on entering the so that's the case. Say if this flag 1 is always false, doesn't matter, so I never have to wait. I'll set my flag to true, use the critical section, set it to false. Again, if I go back, if the other process is not willing at all, I need not have to wait. Again, I come back, set it to true, and keep on doing that. So I can keep on repeatedly using it. And even if this process has not entered even a single time, have you got the point? So this is the problem. So successive entry is not a problem. But what is the other problem? If one process fails inside the critical section, then the other process gets blocked. Okay, because same means if I set my willingness to true and then somehow I get crashed here at this point, so I'll never be able to set my false to my flag to false. So if the other person comes, then he finds that there's a big problem, so he cannot enter because he will simply get stuck here at this point. Okay, so the progress property is partly resolved. I mean, the problem is solved, but the mutual exclusion is not guaranteed. So this cannot be a solution. So are you getting the problem? So we have got only just two processes, and we have got just one resource, and we are trying to ensure all the four properties using purely algorithmic approach, using pure logic. That's all. And you are every time you are trying to come up with some solution, you are getting stuck. So what can be the immediate modification to this? Immediate modification is because why the problem occurs here, mutual exclusion fails, because you have set this to false initially and you are trying to check it, and both might be able to check it successful and both might enter. So the only way to get rid of it, I mean one probable way to get rid of it is you can bring it outside here. So before the while flag 1 or while flag 0 is checked, let us set the flags, my own flags, to be true. Okay. So before you check whether he is willing or whether he is taking the class, you basically shut the door and then you try to check. So you enter, shut the door and try to see that whether that person is also taking the class. Can that be a solution? Will it ensure mutual exclusion if I bring the flag 0 true and flag 1 true before the while loop? Something like this. Got the change here? So these are small steps which one try to make to ensure a solution which will ensure all the four properties and will ensure consistent access to the shared space. Will it solve the problem? Are you getting me? Will it guarantee mutual exclusion?
No, sir.
No, sir.
Why not? Now, making this flag 0 equals to true and flag 1 equals to true before while, will it still happen that the both process enters the critical section simultaneously? Both are here at the same point of, I mean, at some point of time. Is that possible? Will that be possible?
No, sir.
Simply not, because you see, say for example, P0 executes this flag, P0 executes this flag 0 set to true, gets preempted, and P1 also executes this flag 1 equals to true, and then gets preempted. Now again P0 is scheduled and it checks while flag 1 equals to true. So what you will find, flag 1 equals to, it is indeed true, what it will do now? At this point, what it will do? It will wait. Then P1 gets again scheduled. It will check flag 0 is true or not. Well, it will found what it will find. This is indeed true because this process already set it to true. So this will also wait. Are you getting my point? In the extreme case, both flag 0 is true and flag 1 is true is set, and both process will wait in the while loop. Is that fine? Are you convinced with that?
Yes, sir.
But how long they will wait? How long they will wait? Now, when this flag 1, which is true, will be false, when this flag 1 will be false, only when the process P1 will enter the critical section and it will set it to false, right? And when this flag 0 will be false, only if the P0 is allowed to enter the critical section and it will set it to false. So are you getting some analogy with the problems that we discussed in our last classes?
It's a deadlock.
It's a deadlock situation. So you are waiting, P0 is waiting for a condition which need to be set by P1, and P1 is also waiting for a condition which is need to be set by P0, but none of them can proceed until unless they get that condition satisfied. So it's basically it will not take the system to any other points. It will simply both the process will end up in a deadlock situation. But mutual exclusion, is it guaranteed here? Mutual exclusion, yes. It is definitely guaranteed because you can easily verify and see that it is guaranteed. So now, just now in the second attempt, what we found, mutual exclusion was not guaranteed, but there is a violation of the progress property. I mean, there are other problems. I mean, sorry, the mutual exclusion is not guaranteed, but the progress is more or less fine. But now to ensure the mutual exclusion, we found that deadlock occurred. Okay, so mutual exclusion is guaranteed, but the both process willingness before they executes, so this leads to a deadlock. So this is what it means. So there is a deadlock situation here. So are you getting the problem? So what can be the next change that we can make?
We can change the initial values to get only one.
Yes. What can be the next change? Incremental change.
We change the initial values. One is true and other is false.
See, then, but that can also, if that is the case, you say that I make it to true. So you say that let this be false and this be true, right? That is what you say.
Yes. Yes, sir.
So if this happens, if P1 is not at all willing, then what is going to happen? If P1 is not at all willing, so P0 waits for how long? How long it need to wait?
It never gets a chance then.
Yeah, so then again the progress property is violated. Yeah, you don't end up with a deadlock, but you basically end up with a live lock. That is called live lock. So you know that, okay, I know that once he gets a chance, you will provide me a chance and the things will start. But can you guarantee that how long you have to wait? You don't know. But definitely you know that, okay, this is not a problem. Whenever he is willing, I'll get a chance after he is done. But this never happens. So this is again trying to resolve the problem, but you end up with live locks instead of deadlocks. Is that okay?
Sir, hello.
Yes.
What happens if we declare the shared int flag as true, false?
No, that is whatever you do, you make it true, false. But the thing is, the one which is true, that means you are forcing that person to take the first chance, right? You make somebody, so you want that process, maybe P0 or P1, to be the first person to enter the critical section, and then it starts alternating. But if that does not happen, then the other process just stops.
Sir, we may think as we are giving priority if we given true and false.
Priority? No, we cannot. That is so. There is an underlying assumption. So you cannot make any assumptions regarding the priority of the process, which process should be. So it should be all fair. That is the point. You cannot give any other. So that's why the assumptions are listed earlier.
Yes. Yes.
So the thing is, there is no. So what can be one incremental change is that. So once you see, say, I get back to that instead of make. So this is true and this is true. Say for example, this is true and this is true. Now setting it to true means what you are trying to say that you are allowing. You see, you are setting your willingness. You are setting your willingness, and he also set the willingness. And then after that, you are checking whether that person is also willing. Then you wait. Now if you find that that person is willing, to make sure that the same person, the other person is also not, so both are being too courteous. So to avoid that, what you do here, you basically, if you find that this flag is 1, then you reset your willingness. That is what I mean. So the thing is, here there is no opportunity for a process to back off. Back off means what? I set my willingness. That means I close my door, and I found that. So I closed my door, and I found that TD's door is also closed. And TD also closed the door, and he says that he finds that my door is also closed. So what both of us do? Just stand idle and expecting that somebody to leave. But I say that let me take the class, then I'll open the door, and that situation never happens. So the thing is, the simple thing is, I shut my door, and if I check the TD's door is also closed, then what I do? I basically open my door and take a small coffee break and come back. That's what I can do, right? Are you getting my point? So this is what I do here. I set it to true. If I find that flag 1 is true, that means TD is also willing. Then what I do? I set it to false. That means I open my door. Sleep random means I go for a coffee break. Now sometimes it takes 5 minutes, sometimes it takes 20 minutes. And after the coffee, I again set the flag to true, my flag to true. I said that again I am willing. Is that fine? So this is a kind of it's a back off algorithm. If you want, if you find that the other person is also other person has also set his willingness, and you have also set his willingness, so you become courteous. That you said, okay, let me just wait for a while. I reset my willingness. I set it to false. Wait for a random amount of time, and again I set it to my willingness, and again I keep checking that. Is that part clear? Hello? Hello? Are you getting me? Hello?
Yes, sir.
So what do you think? Will it solve the problem? Resolve the problem? First of all, will it ensure mutual exclusion? Will it ensure mutual exclusion?
Yes, sir.
Definitely, because see, ultimately what you did is nothing but setting the flag to true, and then not actually coming to this point till the other flag is false, right? Till the other flag is true, you are not coming. So if it is false, only they were coming. So you are still doing the same thing. So mutual exclusion is definitely guaranteed. But what you try to avoid is the kind of deadlock situation. So deadlocks are avoided, but can it ever happen that uh, both of the faculties take the same amount of time to have a cup of coffee? That is quite unnatural and something very hypothetical, but still, like, both the processes are generating random numbers, and because they have considered the same seed value, so both generates. If I generate 3, you also generate 3. If I generate 4, you also generate 4. So can it happen by chance? And if that happens, so then what is going to happen? Will they be uh, able to enter into the critical section?
No, sir, they'll keep having the coffee.
So now they will have a copy, come back and set it, and again find okay the other person is there, again go back. So the thing is they will be just repeating the same set of steps repeatedly, and so what kind of situation it is? I mean, will you call it as a deadlock? Will you call it as a deadlock? Deadlock means you don't have any hope of getting rid of the situation until unless you backtrack. But is this a deadlock? This is not a deadlock. It's a live lock. Every time you go away with a hope that okay, probably either he will come first or I will come first, and I mean if I come first I'll get a chance, right? Hello.
Yes, sir.
So the thing is, now this mutual exclusion is definitely guaranteed, but this situation can lead to a live lock situation. It's live lock. If the process generate the same random number, same random sequence, the processes generate every time, though it's a very rare incident, but the case cannot be ruled out, right? And this can happen because uh, if the growth starts with the same seed, and we really don't know what seed values they have chosen. So this is more or less closer to the solution, but still you have not solved it completely. So the point is, in the algorithmic approach, you see the problem is so simple. You are given with just two processes, and you are trying to ensure the critical section, the, the access to the critical section associated with R, and you tried a different way of different types of logic, and you find that you cannot ensure all the four conditions to satisfy. So this is just to show that how I will not say difficult, but how non-trivial the problem is. Okay, and only with two processes this is the problem. So if you have got n number of processes, you know that how to ensure and verifying the whether it is mutual exclusion is satisfied, whether progress is satisfied. This verification becomes even more difficult. So these cannot go on like this. So there are approaches, the different researchers they proposed long back, and it was Peterson who proposed in 1991 a correct solution. I mean that also for two process, and in fact before that there are solutions that got proposed. Okay, but we'll stick to this one, which is a more simpler version, and this is the key idea here, you see. So what was the key idea? So he basically borrowed both the idea. So first thing is in the second, third and fourth. So the first thing is the first problem, in the first approach, what was very trivial to guarantee, it was mutual exclusion, right? Because you started with a single Boolean variable turn, and turn can either be 0 or be 1. So it is very trivial to say that either process 0 or process 1 will be inside. But the problem was it was strictly alternating. So the thing is he thought of combining both. So he said that why don't we take a shared integer turn, and also we take two flags. So the flags will indicate the willingness state of each process, and the turn will resolve the simultaneity conflicts, right? Can you guess the problem? So thing is we are trying with flags, and we found that okay, this can be managed if we maintain two flags, each storing the willingness of a particular process. So this is possible, but every time you are either ending up with live locks or deadlocks, and if you try to resolve both, you cannot ensure mutual exclusion. So the thing is, it will be nice if we can combine both of these. So, and that's why that is how Peterson came up with two process solution by combining both the use of turn and flags. Okay, so as it says, use two variable and willingness and the mutual correspondence. So what it says is that flag 0 equals to true. That means it says that I am willing. Okay, and after I am willing, what I do here, turn equals to, he says that I am willing, but the P0 gives the turn to the other process. So it says that it is your turn. I am willing, but so I just say that I am willing, but it is your turn. Now what it checks, that if it is the other process's turn and also if the other process is willing, that means this P0 need to wait. Are you getting the point? So the only change is we just add this step which we borrowed from the first attempt, and we considered this step also as a combined decision along with flag 1. That is what we made. And in the similar way, process P1 also will, after setting its willingness, it will set the other process's turn to true, I mean it is 0, and it will check whether the other process is willing, and also, and it knows it has given the turn. So even if it has given the turn to the other process, if the other process is not willing, it can easily enter here in the critical section. Okay. So will this ensure the mutual exclusion? Have you got the solution? Combining the effect of both.
Yes, sir, it will.
It will, because now again turn is playing the trick and you don't have to think a lot before answering that the mutual exclusion is guaranteed. But what about the deadlocks and all? Deadlocks or live locks? Will there be deadlock situation? That is also not there, because even if you set your willingness, you are giving the other person the turn. Okay, so now the point is, before, I mean, the only thing is the deadlocks can occur if both get stuck in while. So even if both get stuck in while, you see the flags might have both true or both false, doesn't matter, but the turns cannot take same values. Is that correct? So turns is either 0 or 1. So even if both the processes are checking while, the getting stuck in the while loop, so it cannot happen that both gets stuck in busy waiting in that while, right? So the deadlock situation will never occur, not even the live lock situation. And interestingly enough, so if a particular process is willing to enter too frequently compared to the other process, that also will happen. So it will simply overcome the basic problem of the first attempt. Because if the other process is not willing, so it will not set its willingness. And even though if you set your, if you set, give the other process the its turn, if he is not willing, he will not set, I mean his willingness is not true, so you can simply skip that while loop. That means in other way it's saying that I have given you the turn, and still if you are not willing, so let me enter and access the critical section as many times as I want, right? But if both are competing and both are willing to take the class, then how it will occur? It will be strictly alternating, because one turn will be 0 and 1, 0 and 1, like that. So if both are competing, it will be strictly alternating. If only one is willing, the other is not at all willing, so the person or that particular process will keep entering as many times as it wants. Is that okay? So mutual exclusion is guaranteed, mutual blocking is also prevented, monopolization is also prevented. So in fact it solves all the related conditions, and it satisfies this solution. But then extending it to n number of process solution, that is also there, but we take a different kind of algorithm which is proposed by Lamport. This is Lamport's bakery algorithm to resolve to solve it. So Lamport proposed it in 1974. So the thing is, as you can see here, this Peterson's algorithm was in 1981. So it was not, so Lamport's solution was not after this. So it was proposed prior to that. So I just talked about this Peterson's algorithm because of the continuity or the similarity with the attempts that we made to solve it. Okay, but even before Lamport's solution in 1974, there are, I mean, the two process problem was solved by other researchers. Okay, So this is a better way to realize a in-process solution compared to extending Peterson's approach. So that's why we'll stick to this. Okay, so I need another 10 minutes. Is that possible, or is just almost 1 hour? So I stop it here. So this will be the last algorithm in the algorithmic approach, and it will be done. So in the next class I can start with the semaphores. So may I continue, or I'll just stop the class? What is the overall opinion? Hello? Say whatever you feel, because there's no point of extending if you are not willing, or if there are some other problems. May I continue, or I continue it in the next class? Say a yes or no. Hello? Hello?
So you can continue in the next class.
Okay, fine. So it's better you try to settle it down, and I'll pass on the slides, okay, so that you can have a look into it. It will not take too much time. So after we complete this part, I think in the next class, the main focus will be how we create this shared memory, this shared resource. We just say that shared int, shared resource, but it's not easily done as it is said. So we have to write a additional piece of code to make it shared, because we know that nothing is actually shared between two processes except the file handlers, say the file descriptors, right? So how I make a small piece of variable, a small piece of, or a array shared, so that multiple processes which are not even having a parent-child relation, they can have access to it like normal say memory locations. So that will be interesting to see. And once we do that, so these things that we although it looks like a code, but these are not actually the codes. So these are more hypothetical or pseudo codes. So you will be able to write something like that. And par begin also, this is again a hypothetical one, and you know how to run processes parallelly. So that will be the focus in the next class.